Good morning, everyone. I and my colleague, Pan Yuxuan, will have a speech on the China Mobile's big data system. We create the data warehouse system from 2001. And from 2010, we create the big data system on the Hadoop. So this morning, we will show some experience for us. So first, let's introduce some big data system in the China Mobile. The big data, here is some data in the China Mobile. We have nearly 900 million customers in the China Mobile. We are the largest telecom operators in the world. We have 3 million base stations, maybe the largest networks in the world also. And also we have 200 million IoT, Internet of Things connections. In China Mobile, we create 100 PB data per day. So it's really a huge system. In the China Mobile, we have more than 2,000 IT systems. So it's really a difficult works for us to collect all of the data from different IT systems. So the Hadoop in the China Mobile is a big centralized control cluster. We call it CBA Cluster. It has 1,600 and 600 nodes. This is the cluster in the headquarters. In China Mobile, we have 31 province company, so and also some sub company. We have several small computer clusters in each province. At this time, for China Mobile, we have a headquarters and also several big data system in the province in the futures. So we call it 1+N architecture. Altogether, in the China Mobile, in the whole nation, we have more than 15,000 Hadoop nodes at this time. The capacity is more than 500 PB. So that is some introduction for the CBA and also some experience in the construction. And in the end, we will have some future works. This is about the CBA project. We centralized business analysis. The BI system based on the enterprise data warehouse for the group company. In the China Mobile, I just told that we had a headquarters in Beijing and also 31 sub-company in the different provinces. So at first we create the big data system in each different province. And now we are trying to centralize the data to the headquarters. That is the CBA project. The data resources in the China Mobile include the 2 generation and 3 generation and also the 4th generation data from different telecom networks. And also we have some data from the double line. We can take all of the log just to show the user's behavior from the networks. And also we have some detailed data traffic information that can show the condition about the network. We have, just as I introduced, that China Mobile has a huge and difficult networks in the telecom. We also have some customer information, just like the CRM system, the customer's relationship management system. And also we have some service record, like the CDR, the detail record. That can show us that at what time, who make a phone call to the others. And also we use the web crawler, can find some data, collected data from the web. We have some applications, and in the national level, we have 60 unified data model, and in all the nations we have more than 1,000 of different data model. I mean the data mining model in different field. So in the China Mobile, we mainly make our application on the financial, security, and tourism, traffic, advertisement, and healthcare. So at this time in China Mobile, mainly application is tourism and traffic, because China Mobile has the larger. China Mobile in China, we take more than 70% telecom market in China. So it's really huge. We can find the customer's behavior and the location. We can do some online behavior analysis to find the customers, what's the content does the customers like. And also some internet option analysis. So we can see at what time the customers can visit different website and their feature. Also, we have some customers' portrait, and also inquiry of call records. So in China Mobile, we have huge data, and also we can make a lot of applications. This is some brief history of CBA project. At the first stage, in the 2016, we have created only 600 nodes. And in the Hadoop, we have only 400. The other is for the MPP database. So the second stage is 2017. We have more than 16,000 nodes. And in the end of this year, we will have the max Hadoop node is 14,000 nodes. So it will be very huge. And in the future, the nodes will be more and more. And this is the structure of the CBA. The largest Hadoop cluster at this time in the China Mobile is 16,000 nodes. And we have 380 million Hadoop fields. Total capacity is 62 PB. This is in the headquarter. I mean, altogether is more than 500 PB, all the China Mobile. And each day we have 2 PB input data. So, and also 20,000 jobs per day. 14 million fields into HDFS by Flume per day. So it's really a huge data for China Mobile's big data system. And this is some version of the component in the Hadoop. We use nearly a new version of the Hadoop. Almost the almost all of the Hadoop components was used in China Mobile. So the next part, I will introduce my colleague, Pan Yuxuan, to give us an introduction.
Okay. Good morning, ladies and gentlemen. Thanks to Dr. Duan with the introduction of the CBA cluster. And then let me talk about the experiences we learned in the construction of the cluster. And I'm a software engineer majored in big data, Hadoop, and big data management of CMCC. Today, I'm very delighted to have the opportunity of making this presentation to share the practice of large Hadoop cluster in CMCC. Okay, the biggest challenge we meet are the large amounts of data and massive data types. We must build the whole cluster in several months from nothing. So from the deployment stage, test stage, to the production stage, we have taken a fair amount of detours and have several turning points. This page highlights what we've done in this project. We concentrate on data collector with circle-based Flume Interceptor, HDFS tuning, and cluster deployment and maintenance. So let's talk about Flume first. We need Flume to do some operations before sending data to HDFS for some security cares. The data from gateway is compressed by gzip, so Flume should decompress the data in memory first, and then each line of the data should be filtered by certain fields based on different data models. And the next thing is field normalization, which means we need to apply some rules for different fields and make the data standardized. The last important action is called encryption. But why we need encryption here? The reason is that the original data contains some privacy fields, and the most critical data is phone number. So we must encrypt the phone number first. Okay, and of course, all these operations must be done in memory. We choose to use Flume to do all of these things, but there are several problems occurred if we hard-code all the processing logics in the Flume Interceptor. Performance is the biggest challenge, and there are only 50 MB per second per node. So as a result, we need 400 nodes in all to satisfy the data access requirement. Furthermore, the other problem is that Flume agent becomes unstable with GC overhead because all of the process were in memory. So we did different things in the different interceptor in the previous day. Here, one for filter, and one for normalization, one for encryption. And then we linked them in a serial. Actually, it's a traditional way to use Flume Interceptor. But based on Flume standard interface, the input and output of Interceptor are event. In fact, the event is a byte array. Every interceptor needs to deserialize the event to string first, then process the string, and serialize the string to event at last. Through that, the records will be serialized and deserialized 3 times during the whole process line. So it will spend a lot of CPU and produce many intermediate objects, which will cause GC overhead. Now let's talk about the new circle-based interceptor. In my opinion, circle is the best way to deal with the structured data. And we can use UDF, which refers to user-defined function, to implement certain logic. It means all the processing logics can be implemented by one circle. So we use Hive circle here to parse the circle and get query plan. Hive engine will produce the below operator link. First, filter operator. This operator is used to process where clause of the circle for data filtering. And the next one is called a select operator. This operator is used to process the select clause, including expressions and function operation. And the last sync operator is responsible for converting record object to Flume event. As we know, that Hive can parse circle to MapReduce jobs, but in this case, we only use Hive parser to get the operator link, which can be executed locally, so there's no dependency on HDFS and MapReduce. And now let's see the serialization and deserialization in Flume. In the past, we converted byte array to string directly and used string split to get the column value. This spent more than 80% CPU on serialization and deserialization. But after we introduce Hive-based Interceptor, naturally, we start to use lazy simple serialization and deserialization from Hive. The lazy simple one has several advantages. Instead of treating all columns as string, it outputs only typed columns and creates objects in a lazy way to provide a better performance. But it's not enough for us to use the lazy simple one only. Most of our records will have about 200 columns, and not all of the columns need to be normalized or encrypted. So we also develop a new serialization and deserialization tool based on the lazy simple one to merge unprocessed fields. So let's look at the below graph. For processing the column 7 and column 12. Now we only need to got the 7th and 12th column by the delimiter order. The column 1 to 6 and column 8 to 11 will be recognized as a whole, and the serialization and the deserialization will only be applied to the column 7 and column 12. So you can see we get improvement of time performance twice. And here are some other tunings for Flume. First, we use concurrent linked dequeue instead of linked blocking dequeue in memory channel of Flume. Linked blocking dequeue has a lock inside, which will limit the throughput of Flume, but the concurrent one has no lock and it based on compare and set. This adjustment is supposed to make a throughput improvement 2 or 3 times in our scenario. And the second tuning is about Flume channel capacity. This capacity means the number of events can be stored in the memory channel. In general, the throughput capability of Flume sync should be bigger than that of Flume source for preventing data backlog in the memory channel. Usually the channel is empty, so if the network fluctuation occurs by accident, the channel will make the input and the output smoothly. But the channel capacity is not the bigger the better, because when the channel size becomes more than 10 GB, it will cause heavy GC overhead. In our experience, the channel capacity should be less than 5 GB, so we configure the parameter to 2 million in our case. And there are 2 other parameters needed to be adjusted. First is called memory channel keep alive, and the second is called HDFS idle timeout. Memory channel keep alive keeps source for a moment when channel is full instead of reporting error immediately. So we change the value from 3 seconds to 24 seconds, because this value should not be too large of the timeout retransmission. And as for the parameter HDFS idle timeout, it makes Flume close the file if there's no input during the whole idle time. But the default timeout is 1 minute which will produce many small files in HDFS. So we make several rounds of tests, and at last we adjust the value to 600. And this tuning will reduce 70% small files. And we also improve JVM performance by adding some JVM options. Through all of these tunings, the performance of Flume have a big improvement from 50 MB per second to 790 MB per second per node. And the tuning of Flume help us to save a lot of cost because we only use 90 nodes to satisfy all our data. And next, let's talk about the challenges of HDFS. The biggest challenge is the stability of Namenode. We all know that when HDFS file number grows, the memory consumed by Namenode will also grow. As a result, we have 300 million files in a NameSpace, and Namenode memory usage is over 150 gigabytes. A large heap size will cause long-time GC to stop the word. And too many files will bring more RPC calls from application clients. So Namenode RPC performance will become the bottleneck of the whole system. One Namenode should process 30 million RPC calls per hour, and when the cluster is busy, RPC response is over 10 seconds. The worst thing is that the heavy load of RPC core will finally cause the shutdown of active Namenode. Although we have high availability in Namenode, but by the influence of some code bug, deadlock occurs when Namenode fail over in high concurrency situations. So the standby Namenode cannot promote itself to become active state. In the last, we have to restart all Namenodes when active Namenode fails. So Namenode always goes down due to the heavy pressure. When we restart Namenode, it needs 2 hours for each time, because starting Namenode will load the file system metadata into memory first, and then process the block report from thousands of data nodes. These actions are time-consuming in large HDFS cluster. More than 2 hours downtime is in the production cluster is unacceptable. So the HDFS stability is a serious problem we need to solve. And we use this picture of Jackie Chan to express our feeling. And in the last, we have used the HDFS federation with 2 namespaces. Namespace 1 is used for high Flume and applications, and namespace 2 is only for applications. The previous division cannot meet our pressure requirement, so we scale the namespace from 2 to 5, 1 for Hive, 1 for Flume, and 3 for applications. In this way, the pressure of each namespace is reduced, and the failed namespace will not influence each other. And we also find that there are over 100 million yarn logs in HDFS. Previously, we store yarn logs for 10 days in HDFS to occupy large amounts of HDFS resource. So we introduced a log tool in Apache Ambari, which is called a log search, and write yarn logs to Apache Solr instead of HDFS. In this way, we don't need to save these logs for a long time, and we can use the tool log search for further analysis of these logs. The memory used by Namenode is nearly halved from 160 gigabytes to 90 gigabytes by splitting the namespace and removing the yarn logs. And the next thing I want to introduce is called FairCallQueue. Let's revisit this RPC call queue in the old version of Hadoop first. It's a single-line queue. When the queue is congested by RPC calls, the Namenode is overloaded and fails to respond. The RPC latency will become very high, and then have a significant impact on data collection and may cause Hadoop jobs failure. Our cluster is a multi-tenancy one, and we find that most RPC calls are from batch job users, but Flume task requires low latency of HDFS to prevent losing data. So Flume user needs higher priority of accessing HDFS. We use FairCallQueue, which has 4 queues inside with different priority. For Flume task, it need to put it will be put to the high priority queue if having few RPC calls. And for batch job, it will be put to the low priority queue if having massive RPC calls. With the help of RPC-CallQueue, the latency of RPC from Flume decreases from 10 seconds to half second. If you have interested in FairCallQueue, please refer to the below Jira link for more detailed information. And then let's talk about the Namenode GC algorithm. In the past, we used concurrent max sweep GC for Namenode. Most of the time, it works very well. But as the memory usage of Namenode becomes larger and larger, which is almost 200 gigabytes, the time of full GC increases as well as the CPU cost. Sometimes we caught the concurrent mode failure for full GC. What happened is that the object allocation was faster than the garbage collection efficiency. So the older generation of JVM heap was full before the CMS GC finished. This is called a concurrent mode failure in CMS GC. So to avoid this kind of failure and to suspend the GC time, we make a comparison between CMS GC and the new kind of GC algorithm called G1 GC. And as a result, G1 performs better than CMS in suspending long-time GC pause. Here we take the new generation as an example. You can see GC time reduced from 15 milliseconds to 2 milliseconds with JDK8. And there's another problem we met is about block placement. As is known, each block in HDFS has 3 replications for fault tolerance. Although ideally, all blocks will be balanced in different racks with the help of rack awareness policy. The problem we met is that the number of nodes on each rack may be different. So as a result, nodes on smaller rack will receive more blocks. This will lead to running out of space and heavy load. So we made an analysis about this and found that by using the default block placement in cluster, placement of the first block is balanced, but the placement of a second and a third replication is imbalanced when the racks are not balanced. So to solve the imbalance of block placement in each rack, we implement a new block placement called weighted rack block placement policy. This block placement policy will calculate the probability of block placement on each rack according to the number of nodes on each rack. Then it will calculate the weight of each rack according to the probability. And the higher probability will accompany with lower weight. So at last, it will adjust the block placement by rack weight. As a result, the block placement is more balanced on different racks in our cluster. If you are interested in this, please refer to the Jira link here. And we have some other turnings for Hadoop. First, we change the algorithm version of MapReduce file output committer to the version 2 instead of the default value version 1. This helped a lot if a big job generates many files to commit at the last. And this helped, I'm sorry. In the default algorithm version 1, the commit is a single-threaded and waits until all tasks of a job have completed before commencing. This means such job needs a lot of extra rename operations after all tasks finished, which has performance issue. The version 2 will change the behavior of the job commit. The rename operation will be done in the commit of each task, and the job commit only need to rename a directory to job output. So the new algorithm makes a parallel change, and will reduce the output commit time for large jobs. The performance increased by 40%, as known in the below Jira link. And for Hive jobs, we change the execution of engine to test instead of MapReduce. Test can be thought as a more flexible and powerful successor of MapReduce framework. It's based on the directed acyclic graph, which is short for DAG, and the performance better than MapReduce. And we also merge some tasks in ETL process to reduce HDFS access. So besides tuning the parameters and make some code improvement, we also need some operation management of HDFS. First of all, it's better to set a namespace quota in each HDFS namespace. If we don't do this, memory usage of Namenode will increase along with the increasement of file number, which will eventually cause Namenode shutdown. So we need to limit the namespace quota of the root path of each namespace to prevent the Namenode out of memory. And in our cluster, we limit each namespace quota to 300 million. Then we develop some models to estimate the application RPC producing. And with the models, we can count the RPC cores generated by one application in development environment before pushing it to production. And another operation management is to limit the heavy RPC. What is heavy RPC here? It means this kind of RPC cores will lock the file system for a long time to increase Namenode RPC latency, such as delete operation and get content summary operation of a huge directory. So we should be vigilant of this kind of operation. And now let's talk about Ambari. We use Apache Ambari for cluster deployment and management in our cluster. We improve Ambari with new features such as support Namenode federation deployment and high available of Ambari server. And here is an example of 2 federation namespaces deployed with Ambari. And the biggest challenge we faced is that Ambari Web UI becomes very slow when the nodes in the cluster up to 1,600, which brings poor user experience to cluster operation and maintenance engineer. So we need to do some performance tuning as below. Besides the performance tuning, we refer to the community and worked several patches to improve the performance. And the next tuning I want to talk about is called LDAP. LDAP is short for Lightweight Directory Access Protocol. And why we need LDAP here? Because first of all, our cluster enables Kerberized for authentication. If we want to run MapReduce jobs in the Kerberized cluster, we must have a Linux local user created before running the MapReduce tasks in every node manager. This will inconvenient in a multi-tenancy cluster for frequently user add or delete. LDAP can help us simplify the user management, and Hadoop also supports LDAP by changing some parameters. But massive users running jobs in the cluster, the performance of LDAP suffers a lot. The connections to LDAP server is over 7,000, and the latency of LDAP and the latency on LDAP server node over 8 seconds. After analysis of the LDAP, we found that all user and group operations need to set up a connection to LDAP server. So we have 2 solutions for this. First, we take a service called NSCD to catch user information on local. And the second is that we support multi-LDAP server in Hadoop. By supporting multi-LDAP server, we can distribute the connections to different different servers with round-robin policy for load balance. And after the construction of the large Hadoop cluster, we also need a large amount of human resources invested in the cluster operation and maintenance. So we develop a tool called HSmart, which is an intelligent operation management tool to help us maintain and optimize the Hadoop cluster. So this is some screenshot of this tool. With the tool, we can get the cluster health inspection and the cluster resource prediction like this. And the last is job tuning. With the job tuning, we refer to Dr. Elephant at LinkedIn. And we can get some advice for turning the job, such as map GC and map job counters and so on. And at the last part, the last part of today's topic is the FutureWorks. The nodes number changed from 1,600 to 14,000 in the end of this year. So it's really grows very fast. We will face HDFS federation limitation and some others limitation. It's impossible to use a whole big cluster to deal with the limitation of the Hadoop cluster scalability. So we deploy multi-subclusters instead of a big cluster. And each single subcluster will have 3,000 to 5,000 nodes. And we will use some like a router-based federation and a YARN federation to maintain different subclusters. Now I'd like to finish by a short summary about today's presentation. First of all, the challenge we faced is in the construction of large Hadoop cluster, mainly in Flume, HDFS, Ambari, and LDAP. And it's not only follow the community, but also add self-work. Meanwhile, Namenode is the most difficult bottleneck because of the RPC performance. And we also introduce AI into cluster management tool, which helps us to save human resource investment. And in the future, although there may have many more challenges, and we are going to take on them as always. And I think we will have more practices to share in the future. That's all about today's presentation. Thanks for your listening. And if you have any questions, I'd be glad to answer them now. Thank you.